Okay, so today we are going to talk about predicting products of the 5 types of reactions that we saw in the previous notes. So we know from the previous notes there are 5 types of reactions that we can classify based on how the reactants form products. And they include combustion, single replacement, double replacement, synthesis, and decomposition. So the first one we're going to talk about is a combustion reaction because it's sort of the easiest. In a combustion reaction involves a hydrocarbon. So a hydrocarbon, remember, is anything that contains carbons and hydrogens, and they can be in any ratio. These X's and Y's stand for any whole number integers. And remember, you always react the hydrocarbon with oxygen, and your products are always going to be CO2 gas and H2O gas. So there's really no predicting for combustion because it is always going to be these two products. And it's the sort of the easiest, like, freebie sort of reaction because there's no real thinking involved with combustion. Every combustion reaction has the same products. So for example, if you have C3H8 plus O2, it is a hydrocarbon plus oxygen. It is going to make CO2 gas and H2O gas plus energy every single time. Synthesis reaction. Synthesis reaction takes 2 different elements and makes one compound. We saw earlier that it is the marriage. You can think of it as the marriage between 2 elements. You have your A and your B. These represent separate elements, and they are going to merge or synthesize together to create one compound, AB. Most compounds are formed this way, plus these are easily predictable. If you are working with a transition metal and the oxidation is not given to you, you may use the red, white, and blue periodic table, and the most likely oxidation number is the one in bold above the transition metal symbol. If there is more than one bold number, then you go with the higher number because that is the more stable one. So for example, we have iron plus oxygen. Iron is our A in this general format. Oxygen is our B in this format. Notice that oxygen has a 2 there because it is elemental. I'm working on these notes on the speech recap, so you will hear many distractions as I go through these. Oxygen is diatomic, and it is by itself, so that's why that 2 is written there. Now, one of the biggest mistakes people do when they do the products for a synthesis reaction is they say, oh, this is really easy. I'm just going to push the Fe and the O2 together because that should work, right? Well, you know that the elements have valence electrons, and the valence electrons are transferred in a very specific way. So you can't just push those together because that's not the ratio between the valence electrons of iron and oxygen. You actually have to do a little bit of work. If it was that easy, then anyone could do this, but this is honors chemistry, and so obviously it's going to take a little bit more work. So what you have to do every single time is you must write the formula, the ionic formula for iron oxide, where you drop and swap the oxidation numbers properly. So this is where you have to take out your red, white, and blue periodic table. You go to iron, and you notice that iron has 2 numbers above it. One of those numbers is bold, and that bold number is 3. So you're going to put a 3 for iron's oxidation number. Oxygen's oxidation number is going to be 2, and so when you drop and swap this, your formula will be Fe2O3. Notice that the subscripts from the reactants do not carry over to the products. The subscripts on the products are totally independent of what you have on the reactant side. So then why do you start off with 1 iron and end up with 2? Well, that's because that is the ratio that they react. How do you balance it? Now you have to put the coefficients in, okay? So we're going to put a 2 here to balance the oxygens, and then we will put a 4 here. You cannot take the easy way out and just transfer subscripts over. That is like illegal in the chemistry world. Things don't just happen like that. You have to every single time, and this includes synthesis, single replacement, and double replacement. You have to drop and swap to find the formulas of your products. They don't just get mushed, the reactants don't just get pushed together, okay? And the subscripts don't just carry over to the products, okay? It takes a little bit of work. Let's take a look at this. So we have hydrogen and oxygen. You're given hydrogen, which is elemental. It's alone, it's not bonded with anything, so it is going to be H2, plus oxygen, which is also diatomic, which is H2 as well. So again, this is a synthesis because you have A plus B, okay? So here, you can't just push H2 and O2 together. That is not how chemistry works. If it was that easy, then my son in 2nd grade could do this, but it's not that easy. You have to write the formula for hydrogen and oxygen coming together, which is H plus 1 O2 minus, which becomes H2O. Why don't the subscripts balance? Because they don't have to. That is not, nature doesn't care if they balance here, but what you have to do now is put in the proper subscripts to show the ratio in which the molecules react to form the H2O. So you need a 2 here and a 4 here. Your final answer is this guy right here. All right, antimony. Antimony is Sb. It is not diatomic, so we don't have a 2 there. It's going to react with iodine, which is diatomic, so you put a 2 here. Again, I cannot emphasize this enough. These problems are not as simple as pushing the subscripts together. That is the biggest mistake because people don't understand how to do it, so they just do that to write something down. You have to be smarter than that. You have to do a little bit of side work for every single formula you write. Antimony is in group 5, so actually antimony is going to have an oxidation number of 3. Iodine is going to have an oxidation number of 1, so it's going to be SbI3. Next, let's take a look at the opposite of synthesis. The opposite of synthesis is a decomposition. Decomposition is where a compound, a line compound like AB, is going to divorce from each other and create 2 separate single elements. Okay, this one's really easy. Just have to be careful is that if you break into an element AB and one of them is diatomic, you do have to put that subscript of 2. So here we have NaCl. It's going to break into your Na and your Cl. Really, really simple. Double check, are any of those elements diatomic? Yes, chlorine is diatomic, so you put a 2 there. So now you have to balance it with coefficients by putting a 2 there and a 2 there. Okay. And again, I can't emphasize this enough. The subscripts from the reactants do not carry over to the subscripts on the product side. Okay, they are totally independent. They don't. The only thing they have in common are their symbols. Okay, nothing else gets carried over. It's not that easy. Okay, CaI2. So the 2 elements you have, Ca and I. Okay, are either of those diatomic? Yes, the iodine is diatomic, so you're going to put a 2 there. Now, it's just a coincidence that there's a 2 here and a 2 here. That's only pure coincidence. It's not a 2 here because it's a 2 over here. It's just the way that calcium iodide drops and swaps. So in this case, it sort of looks like an easy way, but it did not come from just breaking apart Ca and I2. Okay, and this one is already balanced. Show the decomposition for lithium chloride. So lithium chloride is LiCl. So the decomposition of it is going to be Li plus Cl. Chlorine is diatomic, so you're going to put a 2 there. Go back and balance by putting a 2 here and a 2 here. Single replacement. So single replacement is where you have a single element and it is going to react with a compound, a combined compound, and the single element is going to try to replace either the B or the C. Now, this is the rule. A cation replaces a cation, an anion replaces an anion. So the general rule, you can simplify it as metals replace metals, nonmetals replace nonmetals. The only exception is hydrogen. So hydrogen is a nonmetal, but it is a cation. It takes on a positive charge, so it will replace metals. Okay, so for copper, copper is a cation. It produces a positive ion. Silver is a cation. Cl is an anion. So which element in AgCl2 will copper try to replace? It will try to replace the metal, the cation. Okay. Now, the other thing with single replacement is that in order for this to happen, the copper has to be more active than the silver. It has to be stronger than the silver to break the AgCl2 apart. So how do you determine whether the copper is more powerful than the silver? You look at something called an activity series. So you find copper. Copper is right here. It has to be above what it is replacing. It's trying to replace silver. So we see that copper is more active. The higher up on the list, the more active you are. It has to be above silver in order for that reaction to take place, which it is. So this reaction will occur. So what you end up with is copper is going to be with the chlorine. It replaces the silver, and then you can't just like put the two together and be done. You have to go and drop and swap to find their correct formula based on how their valence electrons interact. So copper is a transition metal. You have to go to the red, white, and blue periodic table. You see that copper's oxidation number, the bold number is plus, it should be +2, even though I have +1 on this old PowerPoint. We'll just say it's +1. Chlorine is +1, or -1 rather. Drop and swap. Your formula for copper chloride is CuCl. And then the silver gets put out by itself. Okay, you do need to balance it when you're done. Multi-steps, multi-levels. So you put a 2 here, a 2 here. Okay, so for a single replacement reaction, step 1, figure out what the single element is going to replace. Step 2, look at the activity series to see if that will actually happen. And then step 3 is to write the proper dropped and swapped ionic formula. Okay, let's take a look at this. Iron plus copper nitrate. So iron is our cation. This is like our A. And then copper nitrate is like our BC. So is the iron going to replace the copper, or is it going to replace the nitrate? Well, copper is a cation. Nitrate is an anion. It has a -1 charge. So the iron is going to replace the copper. Go to the activity series. Iron the single guy has to be more powerful, has to be stronger. The iron is here, the copper is down here. So will this reaction occur? Yes, it will. Iron is above copper. So iron gets to be with nitrate. You look at the activities, or not the activity, you look at the red, white, and blue periodic table. You see that iron's bold oxidation number is +3. Nitrate is polyatomic, and its oxidation number is always -1. Drop and swap, and you get FeNO3, and then the copper is off by itself. You do have to balance this by putting a 2 here, putting a 3 here, a 2 here, and putting a 3 there. Okay. All right, let's take a look at this one. This is chlorine plus sodium bromine. Chlorine is an anion. Sodium is a cation. Bromine is an anion. So which element is the chlorine going to replace? It is going to replace the bromine in this case. Now, there's also an activity series for the nonmetals. If you look at this activity series, it only lists the metals. There is an activity series for the nonmetals. It's called the halogen group. So really, you just have to see this is a halogen, this is a halogen. You just have to make sure that chlorine is above bromine on the halogen list. And chlorine is above bromine, so this reaction will occur. If chlorine was below bromine, this answer would be no reaction. But it does occur. It does actually happen. So the sodium gets to be put with the chlorine. You have to write the oxidation numbers, drop and swap, and then the bromine gets put by itself. Why is there a 2 written next to the bromine? Over here, there is no 2. Why is there a 2 now all of a sudden? When bromine is by itself, it's diatomic. Okay, so just keep that in mind. So to balance it, you're going to put a 2 there and a 2 there. All right, let's take a look at this. We have bromine, which is an anion, potassium, which is a cation, iodine, which is an anion. What is bromine going to try to replace in Ki? It's going to try to replace the I. Okay, so then you look at the activity series. Is bromine above iodine? If you look at group 7, you see that bromine is above iodine, so this will occur. So the potassium gets to be with the bromine, and then the iodine, well, let's drop and swap. The iodine is by itself. Again, notice iodine is diatomic, so there is a 2 that is written over there. We're going to put 2 here to balance that, and a 2 there to balance that. All right, let's take a look at this one. Pb plus Al2O3. Pb is a cation, aluminum is a cation, oxygen is a anion. So the Pb is going to replace the aluminum. Go to your activity series next. Lead is here, aluminum is up here. Lead, because it's trying to replace and break up aluminum oxide, has to be above aluminum, which it is not. So the answer to this one is no reaction. All right, let's see. Let's take a look at these. So the chlorine is going to replace the I. You have to look at the halogen list to see if that's going to happen. Chlorine is above I, so it will happen. So you're going to have magnesium with the chlorine. Drop and swap. This becomes MgCl2. And then the iodine is out by itself. Potassium plus ZNO. The potassium is going to replace the metal zinc. Potassium is all the way up here, so it's definitely going to be higher up than zinc down here. So this will be K plus 1, O2 minus. So when you drop and swap, that becomes K2O. Plus Zn. Do not write anything down there because it's not diatomic. Al plus PbNO3. The aluminum is going to replace the Pb. Aluminum is here. Pb is lead, which is down here. So this will happen. So we're going to have Al parentheses NO33 plus Pb. Then you have to balance it by putting a 2 here, 3 here, 3 here, and a 2 here. And we're done. We forgot to balance this top one, so we just need a 2 there. Okay. We are going to go ahead and skip these examples. Actually, go ahead and just do this one. You have one atom of aluminum. It reacts with one molecule of copper chloride. Copper chloride is Cu plus 2, Cl minus 1, so it's CuCl2. Aluminum is going to replace the copper. You look on the activity series. Is aluminum above copper? Yes, it is. So this reaction will occur. You will have Al plus 3, chlorine minus 1, plus copper. And when you drop and swap, this becomes AlCl3. Oops, AlCl3 plus Cu. To balance it, you need a 2 here, 3 here, 2 here, and a 3 here. It says one molecule of oxygen gas reacts to produce one molecule of magnesium, reacts with one molecule of magnesium chloride. We have oxygen gas with magnesium chloride. Magnesium chloride, you have to write the formula for it. You can't just write MgCl. It's actually MgCl2. And so the oxygen is going to replace the chlorine. In this case, the oxygen is not in group 7, so you can't really look at the halogens to determine if this is going to happen or not. So actually this was a terrible example to show you. We're just going to not do this for right now. Let's go ahead and do this one down here. Calcium metal reacts with sodium oxide. Sodium oxide, let's write the formula for it over here, Na plus 1, O2 minus, so it's Na2O, to make calcium oxide plus sodium metal. This one sort of went backwards. Instead of predicting the products, it was just giving you an example of a single replacement reaction where this is A, this is BC, and then it produces AC plus B. Remember, with single replacement reactions, one element trades places with another. Generally, in single replacement reactions, the metal replaces the metal. One exception is that hydrogen will replace the metal because hydrogen is a nonmetal cation. The nonmetal replaces the nonmetal. Usually one of your compounds is aqueous and then the other one will be elemental. And remember, those diatomic ones have to have a 2 written next to them on the bottom. Let's do another one. So we have copper plus HCl. Here, hydrogen is not a metal, but it is a cation, so copper is going to replace that hydrogen. You look over here, hydrogen is here, copper is below it. So this reaction will be no action because copper is not strong enough to break apart HCl. For zinc plus HCl, the zinc is going to replace the hydrogen. And you look for zinc, which is up here, hydrogen, which is here, so this one will occur. So you'll have zinc and Cl, and then the hydrogen out by itself, and the hydrogen is diatomic, so it will have a 2 there. Go to your red, white, and blue periodic table to find the oxidation number of zinc. It is +2, chlorine is -1. So when you drop and swap, this becomes ZnCl2. And then to balance it, you're going to put a 2 right there. Okay. The key for single replacement is knowing which element is more reactive. Hint, for the halogens, you look at the halogen list. The most reactive one is on the top, which is fluorine. The least reactive one is iodine, which is on the bottom. The single in a single replacement reaction has to be more reactive. So the single guy has to be higher up on that list. So here we have chlorine plus KBr. The chlorine is going to try to replace the bromine. You look at the halogen list, chlorine is above bromine, and so the reaction will occur. You will have the potassium with the chlorine and the bromine, which is by itself. For bromine plus KCl, the bromine will try to replace the chlorine. Because bromine is below chlorine, this reaction will not occur. For the metals, you look at the activity series. The activity series will be given to you. It's not something you have to memorize. You just have to know how to use it. As you see, lithium is the most active metal. And as you see, gold, platinum, and silver are non-reactive. The higher up you are on the list, the more reactive and more vigorous your reaction will be. So if you were asked a question, if you have potassium, aluminum, and tin, and they're trying to replace hydrogen, which one will produce a faster reaction? The higher up on the list, the faster the reaction will be. Okay, so copper plus HCl. So copper is going to replace the C. Copper is down here, so this reaction will not occur. For zinc plus HCl, I think we just did this one. Zinc is up here. Hydrogen is here, so this one will, I think we just did this, so this one will produce a reaction. Let's see. Let's just do this one, and then we'll do double replacement. So predict whether copper will replace silver in silver nitrate. So we go to the activity series. We see copper is here. It's going to try to replace the silver. Silver is down here, so this will happen. So we will have copper nitrate plus Ag. Go to your red, white, and blue periodic tables to write the correct formula for CuNO3. You see that copper's oxidation number is 2, nitrate is 1. So then when you drop and swap, this will become CuNO3 2 plus Ag. To balance it, you'll put a 2 here, and you'll put a 2 here. Okay. For this one, magnesium is going to replace nickel. You look at the activity series, magnesium. Magnesium is not on this list. This is sort of an abbreviated activity series, but magnesium is really, really reactive. It's an alkali metal, whereas nickel is a transition metal, so you would find that this does happen. So you'll have magnesium with chlorine and nickel by itself. Magnesium's oxidation number is +2, chlorine is -1. So when you drop and swap, this becomes MgCl2, like this. And to balance it, it's actually already balanced. All right, the last one is a double replacement reaction where two elements are going to switch up. So you have compound AB plus another compound XY, or I think I called it CD before, and the B and the X are going to switch places. So you have A with Y. No, I'm sorry, the B and the Y are going to switch places, and then you have XB. Double replacement, you do not need to look at the activity series, okay? Because whatever is replacing the other one of them is bound to be above the other one on the activity series. So there's no need for the activity series, but what you do need for double replacement is solubility table, which is located on the periodic table, the one that has the periodic table, the polyatomics, and then there's like a little rectangle on the bottom. That is the solubility table. And I'll show you how to use those in just a second. But here you have a compound, Ai, which is AB. You have PbNO3, which I'm going to call it CD because it's just easier to do it in ABC order like that. And then over here, you have K with the NO3. So the K is now with the anion from this guy. And PbI2 is now CD. Okay. The general rule for double replacement reactions is that you mix two solutions together. 99% of the time, they're going to make a precipitate. Precipitate is a solid that forms from two liquids. The other 1%, you will make an acid-base solution. So you have to predict what product is going to make a precipitate by using the solubility chart. On the solubility chart, if something says insoluble, it means it will form a solid. So that means that if it says insoluble, insoluble means solid. If it says soluble, it means that it will form an aqueous solution, which is not a precipitate. Solubility is the ability to dissolve in water. Substances that dissolve in water, such as sugar, are soluble. Substances that do not dissolve in water, such as rust, are insoluble. Metals are insoluble solids at room temperature. Nonmetals are generally soluble. The exceptions are carbon, sulfur, phosphorus are insoluble nonmetal solids. To determine if a compound is soluble, you consult the solubility table. You find the anion, which is the nonmetal second part of the name, then go across to see if when combined with whatever it's combining with is soluble or insoluble. So for example, this is the solubility table. Notice that the side is based on the anion name, nitrates, nitrites, acetates, chlorides, bromides, iodides, sulfates, sulfites. Notice that the top part of the table is written in terms of things that are usually soluble, and then it changes to the bottom for things that are usually insoluble. And what that means for you is that these anions are shown are mostly soluble with certain exceptions on the top part of the table. On the bottom part of the table, notice that these are mostly insoluble with exceptions being the ones that are listed there. Okay. So, for example, if you have a product called silicon dioxide, the anion is oxide. So you go up to the oxides are right here. And you see that it says all are insoluble, which means that anything that oxygen bonds with is going to be solid, unless you have sodium oxide, potassium oxide, barium oxide, strontium oxide, or calcium oxide. So if you have any of those, then they would be aqueous. But if not, it's going to be a solid. So silicon dioxide, because it is not one of these exceptions, means that it is insoluble with oxygen, means that this is going to be a solid. And again, notice that the bottom chart of the table is written in insolubilities with soluble exceptions. The top part of the table is written with things that are soluble with exceptions that would be solid. So let me show you what the second one says. So we have copper chloride. The anion is chloride. So you go over to the chlorides and you see the chlorides are right here. It says everything is soluble with the chloride except silver, mercury, lead, and copper. So copper is one of those exceptions. So it means that anything else except those four metals would be AQ, but because copper is an exception, it means copper chloride will also be a solid. If you had, I don't know, calcium chloride would be AQ because it's not one of the exceptions right here. Okay, so that's sort of how you read the table. So for a double replacement reaction, it occurs when two metallic ions switch places and one of the products is insoluble in water and forms a solid. Use the solubility table to tell if a precipitate will form. The general formula is AB plus CD yields AB plus CB. This downward arrow means that that is your precipitate because it's sort of showing you that the precipitate is solid, so it'll sink to the bottom of your test tube if you were to do this in real life. In this reaction, compound CD is insoluble and forms a precipitate. So in this double replacement reaction, we have AgNO3, that's our A and that's our B. We have HCl, which is like our CD. So the B and the D are going to switch places. So we have, in other words, the nonmetals are always going to switch places, or you can think of it as the metals, just depending on which one you set and which one you're going to change. So here we have AgCl, so the Ag is going to bond with the Cl, and the H is going to bond with the NO3. So you go to your solubility table, and you're going to look up silver chloride. So go back here. You look up your chlorides. All are soluble except Ag, Hg, Pb, Cu. Because Ag is an exception, it is going to be a solid, and that's why you write the solid there, the downward arrow like that. HNO3, so if one is solid, the other one will be aqueous, but you can check it. You have nitrate, so you go over to the nitrate, and it says everything is soluble if you have a nitrate with it. So that's where the AQ comes from. Here's something to point out. If you have two products, let's say A, D, and CB, and they're both aqueous, it means that nothing really happened and everything sort of just stayed floating around because your reactants are always going to be aqueous, so it means nothing really happened. Everything is just still floating around as ions in water. So if this is the case, then that would be no reaction. I'll show you some more of those and a couple other examples. All right, so let's get into it. Let me just look and see two examples. Okay, so we have HCl, and your double replacement reactions are always going to start off as AQ. The reactants are always going to start off as AQ. And the anions, I always just like to switch the anions, are going to switch places. Now, you have to do a little bit of side work. You can't just do HNO3 and AgCl. The cation comes first. H is going to be with NO3. And you have to write their oxidation numbers, +1 and -1. So this becomes HNO3. And then the silver and the chlorine. So silver is here, chlorine is here. Silver is a transition metal. So you go to your red, white, and blue periodic table. You see that silver has an oxidation number of +1, chlorine -1. So the formula is GCl. And you do have to balance it. It happens to be balanced already. Now we have to determine where states of matter are. Do we have a precipitate or do we not? So you go back and you look up nitrates on your solubility table. Nitrates, you'll get used to this, but all nitrates are soluble. So that means that this is going to be AQ. For AgCl, you're going to look up the chlorides. The chlorides are here. It says all are soluble except Ag, Hg, Pb, and Cu. So because Ag is an exception, it means that it will be a solid, and that's what you put. For number 2, we have calcium chloride, which is CaCl2. Double replacements always start off as aqueous. Sodium carbonate is Na2CO3. Na2CO3. If you did not know where that came from, if I was going too fast, go back and review writing ionic compounds with polyatomics. So here, we're going to switch the Cl and the CO3. Let me just erase this up here so I have a little bit of space to write. Okay, so Ca is going to be with the CO3. The Na is going to be with the Cl. You always write the cation first. If you're wondering why I put those first, write their oxidation numbers, +2, -2, +1, -1. So calcium carbonate becomes CaCO3 and NaCl. To determine what states of matter they are, you're going to look up the anion carbonates. So go back over here. The carbonates are insoluble except Na, K, and NH4. Calcium is not an exception, so it means that this will be a solid. And then if one is a solid, you can check that the other one will be aqueous. You do have to balance this by putting a 2 in front of NaCl. All right, solution of lead nitrate and sodium chloride have lead, which is PbNO32 plus NaCl. These are going to start off as AQ. The NO3 and the Cl are going to switch places. So we're going to have Pb with the Cl, and we're going to have the Na with the NO3. Pb, got to go to the red, white, and blue periodic table because it's a transition metal to look up its oxidation number. Its common oxidation number is 2, so it will drop and swap to become PbCl2. Chlorine is 1. And again, if I'm going too fast to writing these formulas, go back and look at the writing ionic formulas notes. Na is +1, NO3 is -1, so it stays NaNO3. If you remember, now we have to find the states of matter. All nitrates are soluble, so that's going to be AQ. For PbCl2, we're going to go back and look up the chlorides. The chlorides are all soluble except Ag, Hg, Pb, and Cu. Because we have PbCl2, this one will be our solid. And to balance it, we need a 2 here and a 2 here. All right, last one, barium iodide. BaI2 AQ plus Na2SO4 AQ. The Ba and the SO4 are going to switch places, so we will have BaSO4 plus NaI. You're going to look up the sulfates, barium sulfate back here on the solubility chart. Sulfates are here. All are soluble except PbBa. There it is. So if it is all soluble except that, then that's going to be a solid, and then your NaI is going to be AQ. You can go back and check the iodides. Let's just go back to prove that. The iodides, it does say all are soluble except those exceptions. which we don't have one of those exceptions. So it will be AQ. And to balance it, we need a 2 here, and we should be good to go. All right, so those are the notes for predicting products of composition, or combustion, decomposition, single replacement, double replacement, and